Okay, so welcome to this next video. In this video what we're going to talk about is the Phospholipase C gamma family of enzymes. Okay, so the structure then for this video, we're going to start off by discussing the basics of what Phospholipase C enzymes are. Then what we'll discuss is the reaction which they're going to catalyze, and we'll discuss that in detail. Okay, then what we'll discuss is the different families of phospholipase C enzymes, and then we'll focus in on this phospholipase C gamma family of enzymes. We'll see the structure of the phospholipase C gamma enzymes, and then we'll discuss how they're going to be activated by receptor tyrosine kinases, and we'll use as an example the epidermal growth factor receptor. Okay, right, so we're going to start off then with a basic discussion of phospholipase C enzymes, specifically what reaction they catalyze. So, for short, phospholipase C enzymes are abbreviated to PLC enzymes, and another name that people often use for phospholipase C enzymes is to call them phosphoinositide specific phospholipase C enzymes. Okay, this just means exactly the same thing. So phospholipase C enzymes, phosphoinositide specific phospholipase C enzymes, are the same thing. And for short, phosphoinositide specific phospholipase C is sometimes abbreviated to PI for phosphoinositide. So what you do is you take the phospho, and that becomes the P. Okay, and then the inositide portion becomes the I, so PI is short for phosphoinositide, and then I'll put a dash, PLC, so this stands for phosphoinositide specific phospholipase C enzymes, but it's the same title, they're the same enzymes. Okay, these are all enzymes which are going to act on phosphatidilyl inositol 4,5-bisphosphate, PIP2, okay, and break it down into diacylglycerol, okay, DAG, and IP3. This is the basic reaction. Now, I want to discuss this reaction now in detail, okay, and we're going to start off with the structure of PIP2, phosphatidilyl inositol 4,5-bisphosphate. Okay, right. Now, to do this, we need to start off with the structure of PIP2. Okay, so before we can discuss the structure of PIP2, what I want to discuss is the structure of phosphoglycerolipids, because PIP2 is a phosphoglycerolipid. And before I discuss what a phosphoglycerolipid is, I'd like to discuss what a phospholipid is, a larger subset of molecules. Okay, so all phosphoglycerolipids are phospholipids. Okay, so we're going to start off with what is a phospholipid. Okay, so a phospholipid then, in order for a structure to be a phospholipid, it has to obey two criteria. Okay, the first criteria is that within your structure you must have one or more long-chain carboxylic acid molecule. Okay, and the other name for long-chain carboxylic acid molecules is to call them fatty acid molecules. Okay, so these are often also called fatty acids. So, you need to have at least one of these molecules within your structure. So let me give you an example of the sort of, let me give you the archetypal example of a long-chain carboxylic acid. So the archetypal example of a long-chain carboxylic acid is a molecule called stearic acid. And stearic acid is the old name for a molecule that would now be called octadecanoic acid. Okay, and although octadecanoic acid is a bit more of a mouthful than stearic acid, it's a more useful name because it tells us exactly what we're dealing with here. It tells us that we're dealing with an 18-carbon fully saturated carboxylic acid. So let's draw this structure here. So here is the carboxylic acid group, and now we need 18 carbons, okay? So this carbon here, the carboxylic acid carbon, is going to count as carbon number 1, the one that I'm now circling in turquoise here. Okay, so we need 17 more carbons. 16 of these are going to be in the form of methylene groups. So, because I don't want to have to draw 16 methylene groups, what I'm going to draw is one methylene group, and I'm then going to put brackets around this like so, and I'm going to subscript this bracket 16. Now what this means is take this methylene group and repeat it 16 times. Okay, so it's a useful trick of getting round having to draw 16 methylene groups. Okay, then after the final methylene group, what you will then have is a methyl group like so, and that will take you up to 18 carbons. So we've got the 1 here, the 16 here, that takes us up to 17, and then the final one here, that takes us up to 18, and that now is 18 carbons. Okay, so this is the structure then of stearic acid, or octadecanoic acid. Now this is an example, the prototypical example of a long-chain carboxylic acid or a fatty acid. And quite simply, the clue is in the name. It needs to have a long chain, okay? A long tail. So you have the carboxylic acid group and then a really long tail, okay? In this case, we have 17 carbons and it's fully saturated. So it certainly is a long-chain carboxylic acid. Now, this long-chain carboxylic acid that you're going to put within your phospholipid structure, this is the lipid portion in the name phospholipid. Okay, we'll come to the phospho portion. Okay, now what does a lipid actually mean? What does lipid actually mean? Well, basically, lipid molecules is the fancy name, the scientific name for fat molecules. Now, what criteria do you have to obey to be considered a fat molecule? Well, basically, you have to be extremely hydrophobic. Okay, wait, why have I written neutral there? That's the other condition. Ignore that. Fat, you have to be extremely hydrophobic. Okay, and this means that you have to interact badly with water. So why do fat molecules interact badly with water? Well, the characteristic feature that fat molecules have is that they have an extremely neutral structure. Okay, and let me explain why that is going to lead to them interacting badly with water. So let's discuss the structure of water. Okay, so if we have a water molecule here, we have an oxygen atom bound twice to hydrogen atoms. Okay, now in each of these bonds, you'll have one electron coming from the hydrogen and one electron coming from the oxygen. Now the question then is, in these two electrons, for these two electrons that are sitting in between the oxygen and the hydrogen, are they directly in the middle between the oxygen and the hydrogen, or are they tilted to one side? Okay, and the answer is they're not sat directly in the middle. Okay, instead they're tilted towards the oxygen atom. So they sit closer to the oxygen than they do to the hydrogen. Now, this is because the electrons that are in this bond are feeling an attraction both towards the hydrogen atom and towards the oxygen atom. Now, the reason for this is that both the oxygen atom and the hydrogen atom have nuclei. Okay, and in those nuclei they have protons. So there are protons in the oxygen nucleus and there are protons in the hydrogen nucleus. Now, protons have a positive charge and therefore will attract the electrons which have a negative charge. Yes, there are the electrons that surround the nucleus which will be obscuring the positive charge of the nucleus from these electrons that are in this bond here. Okay, but they will still feel a net attraction to the nuclei. Now, these electrons then are feeling a pull towards the oxygen nucleus and also towards the hydrogen nucleus. Okay, now there is a fancy word which means how hard an atom pulls electrons towards it within a bond. Okay, and this is electronegativity. Okay, so if we say that oxygen has a greater electronegativity than hydrogen, what that means is that the oxygen atom pulls on electrons in bonds more than a hydrogen atom pulls on electrons in a bond. Okay, so these electrons are going to sit towards the oxygen atom, they're going to be pulled towards the oxygen atom. Now, what does this mean for the water molecule? Because both the electrons in this bond and also the electrons in this bond will be sat towards the oxygen atoms and away from the hydrogen atoms. That gives the oxygen atoms a slight negative charge. Okay, so the oxygen becomes slightly negatively charged. It doesn't get a full negative charge, but because the electrons are slightly closer to it, that gives it a little bit of a negative charge. Okay, whilst both of the hydrogens down here get partial positive charges because the electrons are slightly more away from them. Okay, this gives water a very polar structure, and it allows water molecules to interact with each other very well. So if I draw another water molecule here, like so, basically the same is going to be true in this water molecule. You're going to have a partially negatively charged oxygen head here, okay, and then you're going to have partial positive charges on the hydrogen atoms down here. Okay, now the partial positive charge on the hydrogen atom of this first water molecule up here will be able to interact with the partial negative charge on the oxygen atom of this second water molecule down here. In addition, you have to remember that the oxygen atom in this water molecule actually has two lone pairs of electrons, which are centers of negative charge. So this lovely lone pair here is a nice center of negative charge. Okay, so not only is this partially positively charged hydrogen atom here going to be attracted to the oxygen's partial negative charge, but it's also going to be able to interact nicely with this lone pair, and it's going to form a strong intermolecular bond here. And this strong type of intermolecular bond here is called a hydrogen bond. Okay, and it is a very strong bond as intermolecular bonds go. So, water molecules can interact with each other very well, is the message from all of that. Now, if you ram a water molecule against one of these lipid molecules here, this stearic acid molecule, it is not going to be able to interact with it nearly as well as it can interact with other water molecules. And the reason for this is that this extremely long tail that we have here is extremely neutral. Okay, and that makes it hydrophobic. It means that it doesn't interact very strongly with water. Now, why is it neutral? Well, let's have a look at what we have here. We have carbon atoms bound to other carbon atoms. Why are those going to be neutral bonds? Well, simple. The electrons in those bonds are not going to sit towards either atom because they're bound, well, the bond is between two carbon atoms, okay? So the electrons in a bond like this will feel an equal attraction towards this carbon here, okay, like so, as they will to this carbon here, okay, and those two forces will cancel each other out so that the electrons sit nicely in the middle of the bond, and therefore the bond is neutral, so you don't get these partial charges being produced. In addition, we have bonds between carbon and hydrogen. Carbon and hydrogen very roughly have the same electronegativity, so they pull on electrons equally again. So really the electrons in a bond between carbon and hydrogen sit nicely in the middle. So this structure has no partial charges, basically. So when you ram a water molecule against this, it's not going to be able to interact very strongly. The intermolecular bonds it will form are very weak. Okay, so this is why when you try and mix fat molecules or extremely hydrophobic molecules, extremely neutral structures like this, with water, they separate. Okay, even if you do your best to mix them, they will eventually separate. And the reason is, it's far more energetically favourable for the water molecules to interact with one another rather than the lipid molecules. So what tends to happen is all the fat molecules end up aggregated together so that all the water molecules can remain bound together, basically. So it's not that the fat molecules interact nicely with each other, it's that the water molecules don't want to have to interact with the fat molecules. They'd much rather interact with water molecules. So the two layers separate so that the surface contact area between water molecules and lipid molecules is the smallest it can possibly be, because that's the most energetically favourable way for it to go. So generally what happens is water molecules push fat molecules all together so that fat molecules all aggregate together. But it's not that the fat molecules like to bind with each other, it's that the water molecules like to bind with each other, and they just push all of the fat molecules aside, and all the fat molecules end up aggregated together. Okay, right. So That's what it means to be a lipid molecule then. It means that you have a very large neutral structure that is going to mean that you do not interact very favourably at all with water molecules. Okay, and therefore you're going to end up aggregated with other structures which don't interact well with water. So that's what is meant by hydrophobic here. Okay, right. That was a bit of a deviation, but a deviation that was worth doing. Okay, let's now talk about the second criterion that you need to obey in order to be considered a phospholipid, and this is the phospho portion of the name. Okay, so you need to have a long-chain carboxylic acid within you. That makes you a lipid molecule. To be a phospholipid, the second criterion is that you need to have a phosphate group within you. Okay, and let me show you the structure of a phosphate group. So a phosphate group consists of a phosphorus atom double bound to an oxygen atom, then with alcohol groups coming off both sides of the phosphorus atom, like so, and then a single bond to an oxygen atom which has then acquired another electron via ionic means and therefore has a negative charge. Okay, so that then is the structure of a phosphate group. So to be considered a phospholipid, you need to have both of these within you. You need to have a long-chain carboxylic acid structure and then also a phosphate group within you. And if you have those two criterion satisfied, then you are a phospholipid. Okay, right, so that's phospholipids. Now let's talk about phosphoglycerolipids. So phosphoglycerolipids are a subset of phospholipids. Okay, so all phosphoglycerolipids are phospholipids, but there are other molecules which are phospholipids which are not phosphoglycerolipids. Okay, right, so phosphoglycerolipids have as their sort of backbone structure a glycerol molecule. As the name suggests, glycerol is going to be very important in here. Okay, and all phosphoglycerolipids are based upon the structure of, if you like, the core phosphoglycerolipids. So there is a phosphoglycerolipid from which all the other phosphoglycerolipids are derived. Okay, and this is a molecule known as phosphatidic acid. Okay, so we'll start off with a discussion of the structure of phosphatidic acid. Now, I'm not going to draw you a molecular formula. Instead, I'm going to draw you a few little cartoons to show this. So, phosphatidic acid then, what you have is a glycerol molecule as your backbone. So I'm going to let this vertical line, which I'm now colouring in green, I'm going to let this represent glycerol. Okay, so this is going to represent a glycerol molecule which is going to form the backbone for our phosphatidic acid molecule. Now, glycerol is the old name for a molecule that is now more correctly called propane 1,2,3-triol. And although propane 1,2,3-triol is certainly more of a mouthful than glycerol, it's a more useful name because it tells us exactly what we're dealing with here. It tells us that we're dealing with a 3-carbon molecule where we have alcohol groups coming off the first, the second, and the third carbons. Okay, right. Now, of the alcohol group that comes off the first carbon and off the second carbon, we are going to attach long-chain carboxylic acid molecules, okay, so fatty acid molecules. So these horizontal lines that I'm now going to colour in orange here, okay, these are going to represent long-chain carboxylic acid molecules which have been attached via ester links onto the glycerol molecule at the first and second alcohol groups. Okay, so I'll put Fa for fatty acids. Okay, it's just an abbreviation. Right, so let me just remind you of the esterification reaction, which I think I'll squash in here. Okay, so if we take our long-chain carboxylic acid here, here's the carboxylic acid group, and I'll put R here to mean an arbitrary long chain as the tail. Okay, then we've got our alcohol group that comes from the glycerol molecule here. So this is our orange, sorry, that's our green portion rather, and this here is our orange portion here. Okay, so how are we going to attach this carboxylic acid group onto the alcohol group of the glycerol molecule? Well, what we're going to do is we're going to take the alcohol group off the carboxylic acid group. We're going to take the hydrogen off the alcohol group. We're going to bind those two things together to make water. Okay, that's why this is a condensation reaction. Okay, and then what we're going to do is attach the carbon of the long-chain carboxylic acid molecule onto the oxygen of the alcohol group. And this link that you then produce between the carbon of the long-chain carboxylic acid and the oxygen of the alcohol group is called an ester link. Okay, so this is what we're going to do to the first and second alcohol groups of the glycerol molecule. We're going to bring long-chain carboxylic acid molecules in, and we're going to forge these bonds here, these ester link bonds. Okay, and that's what is up here basically, how we've attached on these long-chain carboxylic acids onto the alcohol groups that come off our first and second carbon of the glycerol molecule. Okay, now that structure that I've drawn so far is not phosphatidic acid. Instead, this is just diacylglycerol, which we'll come back to. This is one of the products of Phospholipase C enzymes. Okay, but to create phosphatidic acid, what we're going to do is we're going to stick a phosphate group coming off the alcohol group that comes off the third carbon of the glycerol molecule. Okay, so this pink dot here is going to represent a phosphate group coming off that alcohol group that comes off the third carbon of the glycerol molecule. Okay, so let me show you how we're going to attach this phosphate group onto this alcohol group that comes off the third carbon. Okay, so here is the alcohol group coming off the third carbon then. Okay, so this is green for glycerol. Okay, and then we're going to attach a phosphate group onto this. So let me draw a phosphate group here. Here is the phosphorus atom at the center, double bound to an oxygen. Here are two alcohol groups coming off either side of the phosphorus atom, and here is a single bond to an oxygen atom which has acquired an electron via ionic means and therefore has a negative charge. Okay, so the first thing to realize is that if I circle this group here, okay, this phosphorus atom double bound to an oxygen atom with an alcohol group coming off it, that group in pink here, this actually looks extremely like a carboxylic acid group. Okay, in fact, if you were to replace that phosphorus atom there with a carbon atom, that would be a carboxylic acid group. Ignore the fact that you've got 5 bonds coming off it, which is absurd for carbon. But just look at the group that I've circled in pink. If that was a carbon, that would be a carboxylic acid group. So, in actual fact, this carboxylic acid-like group that we have within the phosphate group is capable of interacting with this alcohol group on the third carbon of the glycerol molecule in exactly the same way as a carboxylic acid group would. Okay, so what's going to happen is the same reaction. You're going to take the alcohol group off the phosphate group, you're going to take the hydrogen off the alcohol group, you're going to combine those two together to make water. Okay, so again it's a condensation reaction, and then you're going to link the oxygen of the alcohol group off the third carbon to the phosphorus atom of the phosphate group. Okay, and this link here, to draw the parallels that this link has with an ester link, this is known as a phosphoester link. Okay, so that's how we're going to attach this phosphate group onto the alcohol group that comes off the third carbon of the glycerol molecule via this phosphoester link here. Okay, so I'll colour this in red. Right, okay, so that molecule that we've now created is phosphatidic acid, where we have a glycerol molecule with 2 long-chain carboxylic acids esterified to the alcohol group of the first and second carbons of the glycerol molecule, and then a phosphate group attached via phosphoester link to the alcohol group that comes off the third carbon of the glycerol molecule. Okay, right, so the first thing I want to say is that there is not just one phosphatidic acid molecule, okay? And the reason is that I did not tell you what these long-chain carboxylic acids here and here were, okay? I did not specify that. They can be whatever you like, and they don't have to be the same. You know, you could have stearic acid here, and then some other long-chain carboxylic acid, such as linoleic acid or something along those lines here, okay? So there is a huge scope for variability in which long-chain carboxylic acids you want to put here and here. That means that there is not just one phosphatidic acid molecule. Okay, so there are many different phosphatidic acid molecules, but to be honest, which long-chain carboxylic acids you have here do not hugely affect the properties of the molecule. The important thing is that these long chains, which are known as the hydrophobic tails of the molecule, the important thing is that those are really, really hydrophobic and don't interact at all well with water. And that's true no matter which long-chain carboxylic acids you put there. Okay, right. The next thing I want to discuss is what the difference between phosphatidic acid and phosphatidate is. Okay, so I'll just highlight this hydrophobic tail in orange. Okay, and then we'll discuss what is the difference between phosphatidic acid and this other name, phosphatidate. Okay, because people generally don't talk that much about phosphatidic acid. If they're going to talk about it, they talk about phosphatidate. Okay, so what is the actual difference? Well, phosphatidate, strictly speaking, means the conjugate base of phosphatidic acid. Okay, so this is a very general principle for all acid molecules that applies for phosphatidic acid. Basically, let's try and understand why this molecule we have here is an acid firstly, and then we'll come on to what this is. So, basically, even once you have attached the phosphate group onto the alcohol group that comes off the third carbon of the glycerol molecule via a phosphoester link, you still have intact this group that I'm now circling in orange here. Okay, and if you look at that group, that is another one of these carboxylic acid-like groups. Okay, so phosphate groups, if you like, have two of these things, whereas carboxylic acids only have one of them. Okay, so they have two sides. So what can happen is this hydrogen atom that is bound to this oxygen atom here can be donated away into solution. Okay, so this is a covalent bond. It has two electrons in it, one from the hydrogen here. So let's say this one is from the hydrogen, and then one from the oxygen here. Okay, now what can happen is the hydrogen can cleave off, leaving its electron behind with the oxygen. Now when the hydrogen cleaves off, what does it actually have? Well, hydrogen atoms usually just consist of a single proton within the nucleus. Okay, so I'll colour this in here, that's the proton there, with an electron orbiting around it. Okay, so here is the electron here, colour this in E minus, here is the proton here. Okay, now that's the most common isotope of hydrogen, called protium. Okay, there are other isotopes of hydrogen where you don't have no neutrons in the nucleus. So, for instance, the isotope where you have a single neutron is called deuterium, and then when you have two neutrons, that's called tritium. Okay, but those are much, much rarer. The likelihood is that this hydrogen will just have a single proton in its nucleus. Therefore, when it leaves its electron behind, all that's going away is this single proton. Okay, that's the definition of an acid molecule, something that can donate protons into solution. Okay, so this certainly is an acid molecule because it can donate protons away into solution. Now, once the molecule has donated that proton off that oxygen here, that oxygen is going to be left with a negative charge. That molecule that is left over, where you've lost that proton off that oxygen here, and you now have two oxygens with negative charges sticking off the phosphorus atom, that is no longer an acid molecule, okay? Because it can't donate protons away into solution anymore. So this is a running theme for all acid molecules, that once they've actually donated their proton away into solution, they have a negative charge, and they are no longer actually an acid molecule because they can't donate another proton away into solution. Instead, they've actually become a base because this negatively charged oxygen here, or more generally the negative charge, can accept a proton out of solution, and the definition of a base is a molecule which can accept a proton out of solution. Okay, so they are called the conjugate base of the acid molecule. So phosphatidate refers to phosphatidic acid once it has lost its proton. Okay, that's the strict difference between phosphatidic acid and phosphatidate. Okay, now, under physiological pH, which is around 7.45, most phosphatidic acid molecules have donated their proton away into solution and therefore exist as phosphatidic molecules rather than as phosphatidic acid, which is why most people talk about phosphatidate a lot more than they would talk about phosphatidic acid, because most of the phosphatidic acid exists as phosphatidate. Okay, right, so that's phosphatidic acid. We now want to discuss how we build the other phosphoglycerolipids from phosphatidic acid. But before we do that, let's just discuss the fact that phosphatidic acid is a phosphoglycerolipid, okay, and it is a phospholipid. So let's just check it satisfies our two criteria to be a phospholipid. So it has two fatty acids within its structure, so it certainly satisfies the first condition, and then it has the phosphate group, so it satisfies the second condition as well. So this molecule is a phospholipid. Now, all the other phosphoglycerolipids are going to contain this within their structure, which means that all of those will also be phospholipids. Okay, right, so we'll come to phosphoglycerolipids in the next video.